Next slide. The entire mass of the core, greater than 3 solar masses, collapses down to a very small point. When you have a large mass and a very small volume, the escape velocity near the mass point can be more than the speed of light. Because nothing can travel faster than the speed of light, the distance at which the escape velocity equals the speed of light forms a sort of boundary, beyond which no information can get out. We can't see anything happening beyond that boundary, so it is called the event horizon. Maybe there's something that stops the core from compressing to an infinitesimal point, but that something is cut off from the rest of the universe. The black hole is truly black. So how do we detect something that produces no light, is invisible? Next slide. We detect black holes from the effect of their gravity on nearby objects. For stellar mass black holes, we look for those that formed in a binary system, where two stars were orbiting closely around each other. One of the stars was a very massive star that died, and its core became a black hole. If the black hole is close enough to the visible star, the black hole may be able to suck up some material as shown in this painting of Cygnus X1, among the first of the black holes discovered in our galaxy. If the unseen companion is close, gas flows from the visible star we can see to the companion to form an accretion disk as the gas spirals onto the companion. Accretion means stuff accumulating onto something. Friction in the disk close to the companion can cause the gas to get hot enough to glow. The gas very close to the small companion becomes hot enough to make X-rays. Bright X-ray sources are made only by super hot, compact things, so bright X-ray sources are very rare. That's why we use X-rays to hone in on possible black holes. Neutron stars can also produce a lot of X-rays, so we need to find how massive is the companion. We look at the motion of the visible star to see how quickly it and its companion orbit around the center of mass of the binary system. Newton's form of Kepler's third law gives us the total mass of the binary, visible star plus companion. If we know the spectral type of the visible star, we know its mass. The companion's mass then will be the total mass minus the visible star mass. If the companion mass is larger than 3 solar masses, it must be a black hole. In fact, all of the black holes we have found are at least 5 solar masses. The X-rays from the black hole's accretion disk flicker and fluctuate. We can use how quickly the X-rays change their brightness to derive the maximum possible diameter of the unseen companion. A universal rule of nature is that an object cannot vary in brightness more quickly than the time it takes light to travel across the object. Even if the object could change its brightness all over simultaneously, the brightness change would get smeared out over time. Since the diameter equals the fluctuation time multiplied by the speed of the change, and the maximum speed possible is the speed of light, the maximum possible diameter then equals the fluctuation time multiplied by the speed of light. For the black holes, the fluctuation time is very small, so the maximum size of the black hole is just a few kilometers across. If you have a large mass and a very small diameter, you must be looking at a black hole. Next slide. For very strong gravitational fields, Newton's description of gravity becomes inadequate. Einstein's theory of general relativity must be used to describe the gravitational effects. Einstein found that gravity is not a force in the usual Newtonian description of force. Gravity is a result of a warping or distortion of spacetime around a massive object. The stronger the gravity is, the more the spacetime is warped or curved. There's an entire chapter in the textbook about general relativity. For our purposes here, a black hole is warped so much that it disappears from the rest of the universe in a sort of bottomless pit. The rest of the slide are some of the bizarre things we see because of general relativity. Very distant objects called quasars can have their light bent around a nearby galaxy to produce multiple images of the quasar. The nearby galaxy's warped space is acting like a gravitational lens. If the alignment of the quasar and nearby galaxy is perfect, and the nearby galaxy is not too lumpy, you can see a ring of quasar light around the nearby galaxy. Galaxy clusters can have enough mass to warp the light from very distant galaxies, like this galaxy cluster, the yellow fuzzy things, is doing with the distant blue galaxy. See all the blue streaks? The stretching of space-time also means that time will flow slower near a massive object than farther away. Not only is time moving slower, but also light from the object is stretched out, so the light has a gravitational redshift. We can detect this slowing down of time with even something as low in mass as the Earth. Our GPS system takes into account the difference in how time flows up where the satellites are compared to how it flows here on the ground. For a black hole, the light is stretched infinitely far at the event horizon, and time appears to stop at the event horizon as viewed from far away from the event horizon. That means we'd never be able to see anything cross the event horizon. I have more about general relativity in Chapter 6 of Astronomy Notes, including the detection of gravitational waves.